Okay, we're talking about atomic spectra. This is still part of 5.3 in the textbook. The fact that atoms gain or lose energy in chunks or quanta has allowed scientists to figure out how electrons are arranged in the atom. So they figured out by the fact that certain elements were emitting light, they were figuring out how these electrons were arranged. Atoms will absorb energy. When that happens, electrons are raised, or the electrons jump into higher energy levels. As these electrons return to their lower energy level, they're going to lose energy and in the process give off light. And if you remember, electrons behave as waves. Waves do have wavelengths and frequencies which correspond to light. The light emitted by atoms consists of a mixture of very specific frequencies. Each type of atom has its own specific frequency because it has its own number of electrons. In other words, each element has its own specific frequency because it has its own specific number of electrons. It's not a mixture of all the visible light out there. Each specific frequency of visible light emitted corresponds to a very specific color. So again, each atom has a different number of electrons. They're going to, because there's a different number there, different in the outer shell, different on actually what shell it's in, it's going to jump to different levels, fall back to that original level, give off light. So each element has its own specific color associated with it. And that's known as the line spectrum. Light that contains only a certain color because it only contains certain wavelengths of light. Each line on a spectrum corresponds to one frequency of light emitted by an atom. Each element has its own line spectrum. Each element has its own set number of electrons at different orbitals and in different spots in that orbital. So they're going to be jumping differently. Scientists have used their knowledge of light and waves, and that each element has its own line spectrum to figure out that electron is allowed to have only certain orbitals. It's only allowed to be in a certain spot. Those orbitals correspond to different amounts of energy. My next slide will not be on my webpage, but you can see it here. This is examples of some of those line spectrums. You can see the one for sodium, for mercury, lithium, and hydrogen. And we are going to be doing some of this in class. You're going to see the main light emitted by certain elements, and then you use this special gadget and you can see the line spectrum for that element. Orbitals closest to the nucleus, so the electrons closest to the nucleus, are considered to be in the ground state. They're at the lowest energy level. When electrons absorb energy, they jump to higher energy levels and are now in an excited state. The light emitted by an electron, as it transitions from higher to lower energy level, has a frequency proportional to the energy change of that electron. So we're talking about these wavelengths and these frequencies, and every atom has its own electrons at certain levels and jumping to certain levels and falling back to the original. Okay? Therefore, each transition produces a line of specific frequency in the light spectrum. That element's line spectrum or atomic emission spectrum is what it's known as. Like I said, we'll be doing I'm going to be doing a demo for you in class where we'll see this, and then we'll actually heat up some of these elements and see what colors they emit.